Hello everyone, I'm Dr. Brian Macon. Welcome back to the Math Fun Room, your favorite place to hang out. In this video we're going to learn about the law of cosines, and in particular we're going to be solving triangles where we're given two sides and the included angle. Let's get started. Now up to this point we have discussed solving triangles that involve case 1 and case 2, which represent angle side angle, and side angle triangles. In this video, we will learn how to use the law of cosines to solve case 3, where the measure of two sides and the included angle are given, also known as side angle side, which we denote SAS. Before we solve some triangles, let's first consider where the law of cosines comes from. And this won't be a full proof, but we will work through one case to give an idea of how the law of cosines can be developed and the validity to its use. In order to develop the law of cosines, let's do the following. We begin by strategically placing a triangle on a rectangular coordinate system so that the vertex of angle C is at the origin and side B lies along the positive x-axis. In figure A, we draw the triangle where angle C is acute and the vertex at angle A lies at a point with ordered pair B, 0. Now also, the vertex at angle B lies at the point with x-coordinate of side A times cosine of angle C and y-coordinate of side A times sine of angle C. In figure B, we draw the triangles so that angle C is obtuse. And regardless of whether angle C is acute or obtuse, the vertex of angle B lies at the point with x-coordinate of side A times cosine of angle C and y-coordinate of side A times sine of angle C. If we use the distance formula to compute side C squared, we would have side C squared equals quantity of side B minus side A times cosine angle C, all squared, plus the quantity of 0 minus side A times sine of angle C, all squared. Now simplifying, we have side C squared equals side B squared minus 2 times side A times side B times cosine of the angle C plus side A squared times the square of the cosine of angle C plus side A squared times the square of the sine of angle C. Now factoring out the common term of side A squared from the last two terms, we can write side C squared equals side B squared minus 2 times side A times side B times cosine of the angle C plus side A squared times the quantity, the square of cosine of angle C plus the square of sine of angle C. Now the Pythagorean identity allows us to write this last term, the sine squared plus cosine squared equals to 1. So we have side C squared equals side A squared plus side B squared minus 2 times side A times side B times cosine of angle C. And if we were to complete this process to find the square of side B, we would obtain side B squared equals side A squared plus side C squared minus 2 times side A times side C times cosine of the angle B. We could again complete the same process to find the square of side A, and we would obtain side A squared equals side B squared plus side C squared minus 2 times side B times side C times cosine of the angle A. These last three equations make up what we call the law of cosines. The formal statement of the law of cosines says that for any triangle with sides A, B, C, and opposite angles A, B, C, respectively, we have those last three equations we wrote on that prior slide. Now, in other words, we can say the theorem in the following way. The square of one side of a triangle equals the sum of the squares of the other two sides minus twice their product times cosine of their included angle. It's nice to think of the relationship in words so that we're not having to memorize three separate formulas. Another quick note to make here, suppose the triangle is a right triangle with, say, angle C equals 90 degrees, and since cosine of 90 degrees is 0, then this formula reduces to the familiar Pythagorean theorem, c squared equals a squared plus b squared. Now let's consider an example of using the law of cosines to solve an SAS triangle. And this problem wants us to solve the triangle with side B equals 4, side C equals 5, and angle A equals 49 degrees. I've drawn a rough sketch of the triangle and labeled the given information, but please note this figure is not necessarily to scale. We'll begin by finding the missing side A. Now, using the law of cosines, we have side A squared equals side B squared plus side C squared minus 2 times side B times side C times cosine of angle A. Plugging in the given information, we have side A squared equals 4 squared plus 5 squared minus 2 times 4 times 5 times cosine of 49 degrees. Therefore, side A equals square root of the quantity 41 minus 40 times cosine of 49 degrees, and this is approximately 3.84 for the length of side A. Now we will find angle B using the law of cosines. So we can write side B squared equals side A squared plus side C squared minus 2 times side A times side C times cosine of angle B. Now I'm going to solve for the cosine term. So we have 2 times side A times side C times cosine of angle B equals side A squared plus side C squared minus side B squared. Now divide both sides by 2 times side A times side C, and we have cosine of angle B equals the quantity side A squared plus side C squared minus side B squared, all divided by the quantity 2 times side A times side C. We will find the inverse cosine of both sides to solve for angle B. Thus we have angle B equals inverse cosine of the argument. In the numerator we have 3.84 squared plus 5 squared minus 4 squared, and in the denominator we have 2 times 3.84 times 5. Using our calculator, we find angle B is approximately 51.8 degrees. Now, quick note, we just used the law of cosines to find the measure of angle B. We could use the law of sines to find angle B. However, it's preferable to use the law of cosines because it will lead to an equation with one solution, since the inverse cosine returns values between 0 and 180 degrees, where solving for the unknown angle with the law of sines would lead to an equation with two solutions that would need to be checked in order to determine which one fits the given data. Now, our last step in the problem is to find the missing angle C. So we use the fact that angle A plus angle B plus angle C equals 180 degrees. So angle C is approximately 180 degrees minus 49 degrees minus 51.8 degrees, which is equal to 79.2 degrees. Now, one last note is that we could have used the law of cosines to find angle C. However, that would be a much lengthier process compared to using the fact that the sum of the angles in any triangle is 180 degrees.